Okay, how do we make them? That's actually also known chemistry. It's basically a condensation or dehydration reaction of diones like that. And you can readily recognize that when you look at the system with from a different perspective. Well, we've already sort of pointed this out. If you have a nitrogen here, I call this an enamine. And remember, enamines can be, it's a double enamine. It's an enamine in both directions, and it just happens to be closed at the top, so it's a cyclic dienamine, right? One way to look at it. Enamines are made from carbonyl compounds with amines. Okay? Similarly, when you have an oxygen here, it's an enol ether. It's actually a dienol ether. And if you have a sulfur there, it's a dienol thioether. Okay? And these are made from the corresponding enols. Okay? So you can readily envisage that starting with a dicarbonyl compound like this, you can convert them by loss of water, so it's like a condensation reaction, to the corresponding heterocycles. If you think of this dione, so it's a dione where we have basically the 4 carbon pieces over here, and then here we have the 2 heteroatoms that then are the source of the heteroatom in the aromatic compound. If you think of this unit here as an enol, so you take a hydrogen here and put it to polymerization to the oxygen and make an enol here, and then you make another enol on the other side, formally, then you actually have already almost the final product, except that we have OHs on both sides and we have to remove water. And that's, in essence, what happens in these transformations. So if you take this guy with P2O5, it makes the corresponding furan. P2O5 is phosphorus pentoxide. It's the anhydride of phosphoric acid. If you dump in water on P2O5, it will violently react and make H3PO4 by hydrating all of the phosphorus-oxygen bonds. It's sort of similar to SO3, sulfur trioxide. When you dump in water, it will almost blow up. It gets so hot, it starts boiling to make H2SO4. And so therefore, all of these guys are strong dehydrating agents. They'll suck out water out of any molecule that they find suitable. So P2O5 will do that, and we'll just basically go from here to here. It's loss of water. Okay? So what's the mechanism in detail? It's exactly along the lines that I indicated. You first form an enol on one side. Okay? So you protonate on the carbonyl, lose the proton here, that gives the enol. And that enol, intramolecularly, is now facing another carbonyl, which, when protonated, i.e. activated in the usual acid-catalyzed reaction, is now hot, and this oxygen lone pair attacks that carbonyl. That makes the ring. Okay? So we kick out the electron pair, and you see we're almost there. It's the hydrated form of the product, still protonated, so the proton falls off of this oxygen, goes onto that oxygen to turn it into a leaving group. Here we are. Now, typically, so after deprotonating here, notice this is basically a hemiacetal. And when you protonate, this can leave and make a carbocation here. In the cases of hemiacetals, typically we replace water with another alcohol to make a full acetal or something like that. In this case, this guy, once the water has left to make this carbocation, remember this is a carbocation stabilized by the neighboring oxygen. This is totally like in sugar chemistry, that hemiacetal type carbon. In this case, something else kicks in, namely the realization of the molecule that if I lose a proton, so that's E1, okay? Carbocation loses a proton next door, I put in this double bond, I become aromatic. So the driving force for deviating or entering into a new pathway is the aromaticity, not unlike what we saw on benzene. Okay? So we have the additional feature that you can make a cyclic 6-electron array. And so the whole thing is driven in the last step by this deprotonation proton loss to make the aromatic. So here's another example, P2O5. With this guy, you can get this fused furan system. Yields are quite good. If you do this with P2S5, that's a source of, you can think of it as a source of H2S, if you wish. The sulfur adds to the carbonyl, and oxygen is sucked off, and you're turning the CO double bond into CS double bonds. So it's a way of turning a ketone into a thioketone. So it exchanges rapidly, in other words. If you heat this a little bit, this guy will fuse to, just as it did for the furan, but instead of using normal enols, you go through thioenols, but the mechanism is the same, and you get the thiophase. And if you do this for an amine, remember an amine with carbonyl makes an imine can become an enamine, and when then you lose water, you get the corresponding pyrrole system. Okay? Of course, in this case, you need the external ingredient that has typically an alkyl substituent on the nitrogen, unless it's ammonia itself, then you will get the parent. But the alkyl winds up then as an extra feature in the pyrroles because nitrogen is trivalent. But otherwise, it's the same. So we're going through imine formation, then enamine formation. Here's the intermediate enamine, and that guy then attacks the neighboring carbonyl in a way that's totally identical to the one that we used for the furan synthesis, where we used an enol to do this. Okay? So that's pretty straightforward. And that's the major method of making these heterocyclopentadienes and aromatics. What do? Well, they do electrophilic aromatic substitution, and they do them much better than benzene itself. They react as if they were activated benzenes. And so here we have a system that's no longer symmetrical. Benzene, all 6 positions were equal. We didn't have to worry about where it's going to attack because all carbons were the same. Here we have desymmetrized by the presence of the heteroatom, and so we have 2 different alternative positions, either the position 2 next to the heteroatom or position 3. And so where will the electrophile attack? And if I'd ask you tomorrow in an exam to solve that problem, hopefully you would have remembered what we did in chapter 16. Don't fret it. Just figure it out by going through the exercise of writing all the resonance forms that you get. Attack at C2, look at them, see what they look like, then attack at C3, see what they look like, and then you compare the 2 sets. And then you make some educated guess as to where it should go. And if you can't see any difference, then you would have to say 50-50 chance. So what happens? If you attack at C2, you get the electrophile here. This becomes the sp3 hybridized carbon, and so there's the carbocation. This is a sextet. Which is not particularly good, but feasible. Then you can write another resonance form that puts the plus charge here. That's also a sextet, second resonance form. And then you do the winning combination where this electron pair kicks in. Now I have an octet. Strong contributor, octet structure, great. That's a very good picture. 3 resonance forms, 2 not so good, but 1 is really good. So now let's attack at C3. If you attack at C3, this carbon becomes sp3 hybridized, and so you put a plus charge in here. And really, this other double bond is not involved. So this is a sextet. Not great, but we can now kick in also, as we did up here, with the electron pair, and we get an octet. That's a winner. So we have 1 poor and 1 really very good. Up here we have 2 poors and 1 really very good. I would judge top should be better than bottom, but not really totally convincingly so. These 2 scenarios are not very different. They just differ in the addition of one other lousy resonance form, okay, which is a little better. You're spreading out electrons in space doctrine is better up here than here. And so one would predict attack at C2 should be a little better than C3. How does this pan out in practice? Well, you get mixtures often, although indeed attack at C2 in most cases wins. So it's sort of similar to the scenario we encountered with ortho-para directors. We get ortho attack and para attack, and therefore steric reasons, para almost always dominated, but we have to deal with a small amount of ortho in almost all cases. Okay? And synthetic chemists live with that. They separate them and you discard the ortho product. So here it's the same. So nitration, for example, and you can use nitric acid H+, the usual conditions. In this particular case, they used an NO2 plus equivalent, which is this ester of nitric acid. In fact, nitro plus exists in many forms. You can buy nitrosyl chloride, nitrosyl tetrafluoroborate, and so all kinds of NO2 plus equivalents. In this paper, they use this guy. But you can just stick with nitric acid for nitration to generate NO2 plus as an intermediate. And notice this goes at minus 10 degrees because this is such an electron-rich pi system, so reaction is very facile even at low temperature. And indeed, you get a mixture, but attack at 2-nitropyrrole dominates, 50%, a little bit of the 3-nitro, 13%. Other reactions for other heterocycles, you sometimes only get 2 attack. At least the literature reports only that product. It could mean that they didn't bother isolating the side product, and so you don't have a number. Okay? So chlorination, for example, gives 64% of 2-chlorofuran. Notice, no catalyst. Okay? This is so electron-rich that will react with just chlorine itself. Okay? If you don't want to be confused with the situation of do I use catalyst or don't I use catalyst, by all means, to play it safe, throw in a catalyst. It'll just make it better. Okay, something that's already good will be better. So it doesn't hurt. Okay? So that's perfectly fine. We won't mark you down for that. Here is a methyl substituted. Of course, methyl makes this even hotter. Friedel-Crafts acylation. Typically, we use aluminum chloride, but remember, the aluminum chloride function is that of a Lewis acid. Any Lewis acid would do in principle. So here they use tin tetrachloride. You can use magnesium salts, zinc salts, and so on, iron salts. They're all Lewis acids, and you can just stick with aluminum chloride. Okay? That's perfectly fine in a synthetic scheme. And you notice attack is at C2. That position is blocked, and so you only get attack to the right. So pyrrole is kind of special because of the nitrogen lone pair and the fact that it has another proton there, so one can look at the potential for protonation and deprotonation. In other words, look at what we've done in the cases of amines. Amines can be basic, they can also be acidic. So how basic is this amine? And the answer is given by just carrying out a protonation experiment. And indeed, if you can do this in a MR tube, if you take a solution of this and dump in strong acid, protonation actually doesn't happen on nitrogen, it occurs on carbon. You actually get this protonated species here. And that's kind of bizarre until you realize that there are 2 reasons for this. One is this lone pair, it's sort of a diene-amine, is tied up with resonance to the diene system. It's not available as a normal amine lone pair would be. Okay? And that's where all these other dipolar resonance forms come in that put a plus charge on that nitrogen and a negative charge on the carbons. And that's why protonation occurs on the carbon. The corollary, or the alternative explanation that's complementary, is that the product is resonance stabilized. It's an octet. Okay? That gains from stabilization by invoking the lone pair. And so you get this diene-aminium ion. Be that as it may, protonation is not good, actually. And the pKa of the corresponding conjugate acid is quite low, -4, which makes this about as strong an acid as HCl and the like. Okay? So this is not good. If you look at the pKa of the corresponding ammonium, that's 10, because the corresponding amine is quite basic. So this nitrogen is not basic. That's for the conclusion. The short of it is it's not a basic proton. Notice that we've seen unusual protonation sites because of resonance previously. For example, this amide, okay? That lone pair is also tied up with resonance with the carbonyl, and protonation occurs on the oxygen rather than on the nitrogen to make this guy, which provides you with an octet structure. In enamine, similarly, we don't protonate on that nitrogen, we protonate on the carbon that provides you with a resonating iminium ion structure. So that's just having an extra double bond in there, but the principle is the same. Pyrrole, on the other hand, is quite acidic. So here it behaves like cyclopentadiene in a way, because it can make the corresponding anion. And that anion, you can write 5 resonance forms that put the negative charge on all 5 atoms. Right? So it is similar to cyclopentadienyl anion in a way. And the pKa is correspondingly quite low. Okay? 16.5, that's the pKa actually of cyclopentadiene itself, but also alcohols. Okay? So with a reasonably strong base, like tertiary butoxide or anything stronger, you deprotonate and you make the corresponding anion. pKa is 16.5 for this guy. Compare this to the saturated system. That's like a normal amine. You're back to aldehyde. The isopropylamine, pKa is 33. So to make that anion, you get a very strong base. So this is not very acidic at all. But here it is acidic because that nitrogen is sp2 hybridized, and the corresponding anion is stabilized by resonance. There are millions of possibilities now of making larger structures. A lot of them are now coming to the fore in the electronics industry because, remember, just like benzene, these heteroaromatics have delocalized pi systems. If you make them extended organic arrays, you have organic conductors. So we'll just do one of them. Okay? But you can have limitless combinations of benzene rings with the heteroaromatic compounds, be it furan, pyrrole, thiophane, phosphorus-type compounds that are being looked at, and so on. Okay? And so I'm doing an analog to naphthalene where one of the benzene rings has been replaced by furan. And if you look at the total electron count, it's the same. This one has 10 electrons, and this one has 10 electrons. They're both 4n plus 2 with 2 electrons. They're both aromatic. And one way to sort of convince yourself of that is to write all the possible resonance structures, delocalizing all electrons. You can do one just involving the benzene ring, where you move these 3 electron pairs around to get this resonance form, or you can start with the pyrrole and start donating the electron pair in here. That puts a plus charge on the nitrogen, negative charge here, and then that means you have a benzylic anion, and you can start delocalizing that benzylic anion all around the ring and go with that. And that way you can convince yourself, indeed, this is a completely delocalized pi system. It's aromatic. And therefore, since it's aromatic, it should do electrophilic aromatic substitution. And now, since we're blocking with a benzene ring 2 of these carbons, the electrophilic aromatic substitution leaves only 2 positions open. Again, position carbon 2 or 3. Attack at C3 would give you a plus charge here and a resonance structure that has the octet. That's good. And it's particularly good attack at 3 because you're leaving completely untouched the aromaticity of the benzene ring. So this looks like a good camper attack at C3. What about attack at C2? In Pyrrole itself, attack at C2 was preferred. Now attacking at C2 puts, well, you can start with a positive charge here, which you can then transpose over here, and then over here, then over here, and eventually down here. That's the octet structure. And in the octet structure, which is the strongest contributor to the molecule normally, this one is actually not that great because you're disrupting the benzene aromaticity. So here we have a clear-cut choice. In indole, all electrophilic aromatic substitution very strongly prefer attack at C3 and no attack at C2. And now let me give you the highlight of my lecture. See you next week.